So in addition to looking at what appliances cost us to run, I also want to look at how we actually supply the power to these appliances in our home and what that home circuit really looks like. So if you've ever been in your basement or in your garage, you're going to have a circuit breaker box. You have a wire that's coming into your home from the outside, from your power lines, and that's supplying a source voltage and some charge. And it hits your circuit breaker box, and you split that, and you send circuits, basically wires all the way through your home that energize your home, allow you to plug things in, right? So it basically extends that connection to that power line. And so what we end up having to do is, in order to manage the flow of the charge, we split up into multiple circuits. So I'm going to look at what a typical circuit might look like, and I think some of you guys have experienced and had to troubleshoot some of these issues before. But the way things are wired in our home, most appliances are going to get that 110-volt supply. Anywhere from 110 to 120 is what you get in the U.S. Some appliances need more voltage, maybe a dryer in your home or a stove, something like that might need a little more push or pressure. So you might actually have a 220 to 240 volt supply to those. Those require a thicker wire. You'll see in your circuit breaker box like a double bar switch when those are wired. But most of your switches are a single switch, and we'll talk about what those breakers look like. But basically, every circuit in your home, you might have 15, 20 different circuits running through your home, depending on how big your supply is. But let's look at a typical bathroom circuit. Right? So if I have an upstairs bathroom, I'm going to have a wire running from my circuit breaker box up through the walls, up to that bathroom, and coming out of that supply, here's our 110-volt supply out of our circuit breaker box. And that wire actually passes through this device, right, called a circuit breaker. It literally is, there used to be a fuse, which was a thin wire that would burn out if you ran too much current. It would literally melt the wire, and it would be like a switch. And you'd have to switch out this fuse to make the circuit work. Well, now they have these things called circuit breakers that when they heat up due to too much current, they actually open, and it trips the breaker, and it stops current flow through the circuit. And so all the current that's going to run to this bathroom circuit is going to run through a 15 amp circuit breaker, which means if it gets any more than 15 amps, that thing's going to trip, and it effectively opens a switch, which means nothing else is going to be able to get energized. Right? But assuming we're under that limit, we're going to hit a split, and we're going to hit our first appliance. Let's say that's a hair dryer that may or may not be plugged in. Right? Well, that hair dryer is on its own loop back to the source. Right? And let's say that dryer is rated with a power of 1,000 watts. Right? A hair dryer is just a coiled wire that you run current through it. It's very low resistance, and you get high power output. Also plugged into that circuit, we've got some lights, some ceiling lights. Right? So let's say we just got one lamp that's plugged in, and that lamp, it has a 75 watt bulb, right? So 75 watts is its power consumption. We also need to iron our clothes in the morning, right? So we may or may not have an ironing board with an iron. And again, an iron heats things up. So again, it's this coiled wire. You run some currents. It's going to have high power consumption, 1,200 watts. You might need to clean your carpets, right? So let's throw a vacuum in here. All right, or a vacuum cleaner. Can't spell vacuum. I think it might be only one C. Let's try that again. And that vacuum, let's say it's only about 400 watts. Not crazy. And let's throw one more device in here that has its own switch. Our electric shaver. All right, so we got to shave in the morning. So we got our electric shaver. Not a whole lot of power consumption. We'll call it 40 watts. All right, so you have all these possible things that could get plugged in. You might have multiple outlets in the wall in that bathroom. And depending on what's plugged in, you're going to be drawing different power on this particular circuit. So what I want to know is, well, what can I plug in? All right, can I turn all these things on and still run my circuit? And so let's figure some things out. I think we've all been in that situation, particularly maybe in an older home, where you've turned some things on. Maybe you're running the hairdryer, and then your mom flips on that vacuum cleaner. And what happens? Boom! Everything goes dead. The circuit breaker gets tripped, right? And it cuts all power, and you don't have any power in that circuit anymore. Lights go out, the vacuum's off, hairdryer is not working, right? And that's a safety thing, right? And the reason that happens is because you're trying to avoid a fire, right? And so we have this bathroom outlet, and it's got 110 volt supply from it, and it's connected to a 15 amp breaker. All right, so that's my limit that it can take, right? We've got our 5 appliances. We got our hair dryer. I'm just going to label things out here so we can kind of keep track of what we have. We've got a light or a lamp, right? We got our iron. We've got our vacuum. And we got our shaver. And I want to look at a couple scenarios where we're going to have different appliances turn on or off. We know the values again. Our hair dryer is 1,000 watt. Our lamp is just a 75 watt bulb. The iron is 1,200 watts. All right, and we got these values by looking at the labels, just like we talked about earlier today. The vacuum, when it's running, is drawing 400 watts, and your shaver is just a little 40 watt shaver plugged in to the wall. All right, and so let's look at some scenarios. Scenario 1. All right, you have everything on except for the clothes dryer. On. All right, we haven't turned this one on. Everything else is on. Right, so you're drawing power from 4 of the 5 appliances. Scenario 2. All right, the hair dryer is off. The vanity light is on. You got to see some things. Clothes dryer is still off, and we have the other 2 appliances on. And then we'll do one more scenario here. We're off, and then everything else is on. All right, so each one of these scenarios is going to draw a different current out of that supply. Right? It's going to draw more power. Well, let's figure out what this is going to be. All right? And so we can actually, if everything's turned on, we can actually figure out the total power consumption. All right? And so that total power is literally just adding up all of the power of those individual devices. All right? So let's just take those values, add them up, do a little crunch some numbers, and we'll figure out what these scenarios are drawing. So our total power for scenario 1 is going to be 1,515 watts. Scenario 2 is only 515 watts, and scenario 3 is 1,715 watts. All right, and from here, we can actually determine, based on our voltage, how much current is going to be drawn out of that circuit, right? And so we can actually calculate I total, which if P equals IV, then P over the voltage is equal to I total. So if I take that power and divide it by 110, I get 13.7 amps gets drawn. You get 4.6 amps, and you get 15.5 amps. And so here we see a scenario where, hey, I'm going to draw too much current, right? If I have these appliances on in this scenario, we are going to trip the breaker. Again, we are pulling so much charge through those wires. Those wires are going to get red hot, and we risk actually melting through the metal wire and starting a fire in our home. And so that circuit breaker is going to prevent that by opening up our circuit to make sure that that doesn't happen. All right, and so an old house, you'd have to go replace the fuse. And a new house, you just go down, you make sure you turn things off, and then you flip that breaker again. So which one should we turn off if that's the case? So we've blown this breaker. Well, which one do we turn off now? And it's really going to depend, right? You obviously can go back through. Well, if we pick the one with the most power draw, that's probably makes the most sense. Maybe turn that iron off. But how does power consumption relate to resistance? All right, and so that's the other thing I want to look at here, because each of these is effectively applying resistance to the circuit. Right, and so we want to look at which one has got the least resistance, low resistance, high current, and we can actually determine that in this scenario here. So if I know that P equals I times V, we also have a couple other scenarios, right? Doesn't P also equal I squared times R? And it also equals V squared over R. So if I know the voltage and the power, I can actually calculate the resistance of each of these appliances. So let's take this. Resistance then would be V squared over that power. All right, so 110 volts squared over each of those powers, you can actually calculate the resistance. Let's look at what that iron would be. For the iron, the resistance is going to be 110 squared over its power consumption, 1200, right? That's volts, that's watts. And you can actually get the resistance value, 110 squared divided by 1200. You only get 10 ohms of resistance in that iron. It turns out the lower the resistance, the greater the power consumption, and the more it's going to cost you to run. And it kind of makes sense, right? If I don't have much resistance to the flow is going to move really fast, and I'm going to use up a ton of electrons in a short amount of time, right? And so if I actually go back here and I do those same calculations, you can actually see what those resistance values are going to be. If I take 110 squared and just divide it by each of those power numbers, you're going to get some resistance values here. Your dryer, right? A lot of watts, you're going to get roughly 12 ohms of resistance. You're going to get 161 ohms, right? A lot higher resistance for that low power. We just looked at that iron is about 10 ohms. The vacuum is about 30 ohms, right? And we see that shaver, well, it's really low power. It's going to have a pretty high resistance, 302 ohms. All right, so what I want you to try to tap into is that relationship between how much resistance there is and how much power that something consumes. Very low resistance is going to be a high power draw. And these things that have low resistance, like a hair dryer, a toaster oven literally is just a metal wire that you're running current through, and it gets red hot and heats your food. That's what your electric stove does as well. If you open it up, you got that red wire that's running through. It's just connected to two ends of a battery terminal, or in this case, the wires run into your circuit breaker box. Right? So it's going to draw a ton of charge through it in a short amount of time, really high current. So hopefully this kind of identifies some of the things in your home and how things run. All right, everything's wired in parallel, and so you're going to get the same 110 volts everywhere. And in order to supply that 110 volts everywhere, as I turn more and more things on, the total current is going to have to increase. And that's going to allow enough current to get to each pathway to run that device. And so you see how those voltage and current rules come into play here in your home circuit. And so we normally have a circuit breaker set, and depending on what you need for that room, you're going to design it as such that you're not going to blow that breaker. So oftentimes you'll see a whole line where it's just the lights. So you might have your lights on one breaker and then your outlets on another, which is a nice thing to do if you ever got to do any repairs, because you usually shut the power off, and if you shut off the lights, well, you can't see what you're doing. So usually you have those on separate loops as a way to kind of troubleshoot that. If I'm going to have some kind of application with a lot of audiovisual stuff in a den, I might actually have a separate circuit wired just to those appliances to make sure that I don't draw too much power. And the other thing to consider is those extension cords. If you think about it, an extension cord is literally just adding extra outlets to the same circuit. So when you have an extension cord and you start plugging that thing in with 10 different appliances, well, you can see how quickly you might be raising that current and potentially blowing a breaker. So you got to be really smart. Usually it's that space heater you plug in in your room that's going to trip everything off, because again, that space heater is going to be high power consumption, and your room might not be designed to be running a space heater and a refrigerator in your dorm or all these other things. So keep that in mind when you start plugging things into these home circuits. But hopefully this gives you a little bit of idea of what to expect and some practical usage of some of this electrical stuff.